Okay, so it looks like there's something up with how we think the universe works. One of the biggest head-scratchers is how fast the universe is getting bigger, its expansion speed. For over 10 years, scientists have gotten two different answers, which is frustrating. When they look at the universe today, they see it expanding about 9% faster than what they'd expect from looking at stuff from the early universe. Everyone hoped the James Webb Space Telescope, the best telescope ever, would clear things up. But no luck. It's actually made the problem worse with super clear new pictures. This is making some scientists rethink the basic model of how the universe works. Maybe there's something big we're just not getting, so let's look closer to understand these issues with the James Webb's latest super deep images. Basically, the universe started with the Big Bang. Everything was crammed into a tiny space, and then boom. Matter, antimatter, and all that good stuff popped into existence. The problem is, matter and antimatter should have destroyed each other, but for some reason, there was a little more matter than antimatter, and that is why we are here. Then, gravity started doing its thing, squishing the matter and making sound waves ripple through it at crazy speeds. As the universe grew like a balloon, normal matter gathered around clumps of dark matter, forming the first galaxies, all tied together in a big cosmic web. At first, the expansion slowed down. But then, around 5 billion years ago, things sped up again. Scientists think this is due to dark energy, a mysterious force that's pushing everything apart. The easiest answer is that dark energy is cosmological constant, a kind of energy that's the same everywhere and always. As the universe grows, the amount of regular matter gets less, but the amount of dark energy stays the same. Eventually, all the matter will be so spread out that the universe will freeze to death. Most of this model seems to work pretty well, but here's where it gets tricky. Scientists have no idea what dark matter or dark energy actually are. According to Ofer Lahav, most people think 5% of contains ordinary stuff, 25% is dark matter, and 70% is dark energy. The awkward truth is we don't understand because most of the universe composition is dark matter plus dark energy, but we don't understand what it is made of. Even worse, the universe seems to be expanding at different rates, depending on how people measure it. This is called the Hubble tension. Measurements of the early universe show it expanding much faster than what our model predicts. And those measurements are pretty solid. Adam Rees said that the only reason they can disagree, something is missing in our model. So, how do they measure TICE expansion? One way is by looking at the cosmic microwave background, CMB, the afterglow of the Big Bang. The European Space Agency's Planck satellite mapped this and got a really precise measurement. It also let them see how matter clumped together in the early universe due to those sound waves, which allowed scientists to infer amounts of regular matter and dark matter. When they plugged everything into the model, it spat out an expansion rate of about 67 kilometers per second per megaparsec. To try to explain this better, imaging there is a galaxy 1 megaparsec away from us. That means it's moving away from us at 67.7 kilometers per second. At 20 megaparsecs, it's moving at 1,340 kilometers per second. If a galaxy is over 4,175 megaparsecs away, it's zooming away faster than light. Another measuring method involves special stars called seed variables. These stars get brighter and dimmer in a regular way, which helps astronomers figure out how far away they are. Henrietta Swan Leavitt figured out that the brighter it was, the slower it would flicker. This is how they measure how far away a distant object. By lining up these stars, astronomers can make a distance ladder to measure the universe's size. Wendy Friedman said that they start by measuring nearby Cepheids. Then, they use just the Cepheid readings only that are farther away. After that, they look at how much the light from stars and supernovas has been stretched out as the universe grows. This gives them another measurement of the expansion rate. In 2019, Ree and his team used the Hubble Space Telescope to look at a nearby galaxy. They got a much higher number, 74 kilometers per second per megaparsec. But Hubble wasn't perfect for this type of measurement, so some scientists thought it might be a mistake. That's why everyone was excited about James Webb. It could either fix the problem or make it worse. James Webb's mirror is way bigger than Hubble's. It can see things that are much fainter and can see a wider range of light. The James Webb measured Cepheid shows almost the exact same result, 73 kilometers per second per megaparsec, and other scientists measuring with different ways saw a number close to the expected, such as 69.6 to 66.6 kilometers per second. A cosmologist named Rooney K. said that the CMB temperature is measured at the level of 1%, so a difference of 7 kilometers per second from other measurements it is not very much, is very unlikely to be a random chance. There is something definite to explain. So now, cosmologists are scrambling to find a solution. When there was new Hubble data, scientists met to try to resolve this issue, but it didn't resolve anything. Everyone was still on their side, as Vera Rubin said at the time. So scientists came with an explanation, which one measurement errors 2. New physics, 3, or a combination of the two. Because of that, most of the data is pointing at new physics, as said that dark energy wasn't the same in the early. The simplest explanation is that there are other possibilities as well, that dark matter interacts with light, but scientists don't want to have more complex ideas. James Webb not only is solving the issue, it is also a new area. Scientists found out that galaxies was formed like 300 million years after the Big Bang, but Webb found that these primordial galaxies are way more massive and more advanced than the traditional standard. Webb found a lot of heavy elements, and the stars are building very strong structures, supermassive black holes and galaxy formations. The Hubble issue are adding to the problem with the James Webb discovery. Resolving the Hubble issue and understanding better the earlier galaxies might require new physics or revision of the standard world model. It is also the most exciting nowadays to pursue and get these answers. The James Webb Space Telescope JWST has not only revolutionized our understanding of early galaxies, but has also opened new avenues for exploring fundamental questions in cosmology. Capturing light from some of the earliest galaxies formed just 300 million years after the Big Bang. These observations have challenged the conventional wisdom about galaxy formation, suggesting that early galaxies were not just simple young structures but were surprisingly mature, containing heavy elements and harboring supermassive black holes at their core. This discrepancy between theory and observation raises profound questions about the mechanisms driving galaxy evolution in the early universe, leading to the formation of galaxies with unexpectedly complex structures so soon after the Big Bang. Moreover, JWST findings have long-standing puzzles surrounding dark matter and dark energy. These compositions remain poorly understood. Dark matter plays a crucial role in shaping the large-scale structure of the universe. Despite extensive efforts, its precise nature and composition remain elusive, prompting ongoing searches through direct and indirect detection methods. Basically, the universe started with the Big Bang, right? Everything just popped into existence. Then, there was this crazy mix of stuff that should have destroyed itself, but it didn't because there was a bit more matter than antimatter. Then gravity happened, making sound waves ripple through everything. As the universe expanded super fast, some of this stuff spread out. The usual story is that regular matter gathered around invisible dark matter, making galaxies and a big cosmic web. At first, the universe slowed down as it got bigger. Around 5 billion years ago, things sped up again because of dark energy. The simplest idea is that dark energy is everywhere and always the same. All the stuff in the universe, like regular matter, dark energy, and light, sets the speed limit for how fast it can expand. These things fit into our main model of the universe, which says it'll eventually freeze to death as everything spreads out. This model has gotten a lot right, but here's where it gets tricky. Even though we've been looking, nobody knows what dark matter or dark energy actually are. One professor, Ofer Lahov, said it's kind of embarrassing that we only understand 5% of what the universe is made of. But there's an even bigger problem. The universe seems to be expanding at different speeds depending on how you measure it. This is called the Hubble tension. Measurements of the early universe say it's expanding faster than our model predicts. These early measurements have been checked a bunch of times, so one of the astrophysicists, Adam Ree, said the only way these numbers don't match is if we're missing something in our model. Measuring the universe's expansion is tough. One way is to look at the cosmic microwave background, CMB, which is light from when the universe was a baby. The European Space Agency's Planck satellite mapped this light and figured out the expansion rate with very small errors. This baby picture shows the universe was mostly the same everywhere, but with slightly hotter and colder spots. These spots show where sound waves made matter clump together. By studying these ripples, scientists figured out how much regular matter and dark matter there is and got a number for dark energy. When they plugged all this into the model, it spat out an expansion rate of about 67 kilometers per second per megaparsec. Another way to measure the expansion rate is by using stars that pulse called Cepheid variables. A lady named Henrietta Swan Leavitt figured out that the brighter these stars are, the slower they pulse. This lets scientists figure out how bright they really are and how far away they are. Using these stars, astronomers make cosmic distance ladders, taking them further back in time. Wendy Friedman, an astrophysicist at the University of Chicago, said the distances are added using Cepheid readings alone. Then, they look at how much the light from these stars and supernovas has been stretched out as the universe has expanded. This gives another measurement of the Hubble constant. In 2019, Ree and his buddies used the Hubble Space Telescope to look at a nearby galaxy and got a crazy high expansion rate of 74 kilometers per second per megaparsec. But Hubble wasn't precise enough because the space was crowded, so some stars blurred together. Some scientists still said that the results could be a measurement mistake. So, when James Webb launched, everyone hoped it would either fix the problem or make it definite. Webb's mirror is way bigger than Hubble's, so it can see fainter stuff and is better at seeing different colors of light. Ree and his team used Webb to measure Cepheid stars in another galaxy and got nearly the same result. Other measurements also came back with close results. Scientists were pretty shocked. According to Rooney K., a cosmologist at the University of California, the odds of these results being a fluke are super low. Something needs to be explained. The new results split scientists into teams chasing different ideas. After the Hubble results, there was a meeting to try to solve the problem, but it just made things worse. As one of the scientists, Vera Rubin, said, everyone was stuck on their own ideas. So, when James Webb and another Hubble result came out the next year, scientists had three options: measurement errors, new physics, or a mix of both. Kay said that most data points to new physics. The simplest idea is that dark energy is acting differently now than it was in the past. Dark energy and dark matter aren't the only head-scratchers, though. James Webb is also used to see far back in time. It found galaxies that formed super early, but they're bigger and more grown-up than our model says they should be. These galaxies have lots of heavy stuff and big black holes. These findings have made the debate more intense by confirming the old problems and showing new stuff about early galaxies. It might take new physics or a big change to our model to solve the Hubble tension and understand these early galaxies. The James Webb Space Telescope has changed how we see early galaxies and has made it possible to look at basic questions in cosmology. It's seeing light from the earliest galaxies, which are surprisingly mature. This makes us wonder if galaxies grew faster than we thought. Webb's findings have also made the dark matter and dark energy puzzle bigger. We don't know much about these things, even though they make up most of the universe. Dark matter shapes the universe, but we don't know what it's made of. Dark energy is making the universe expand faster, but it might not be the same everywhere. Some scientists think it changes over time. Solving these questions will take new telescopes and new ways of thinking. Scientists are thinking about new theories and new particles. Webb's discoveries could also help us understand where planets come from and what it takes for life to get started in the universe.